This is Lecture 5. We're going to be discussing the graphical display of data. Let me remind you the context we've been talking about. We're going to imagine that we have a population of individuals we're interested in, and we have a variable, some question that we can ask of each individual. And we'd like to summarize that data. More frequently, though, we'll be in the more precise situation we've talked about, where rather than having access to all of the population, you only have access to a sample, a subset that you hope is representative. So we're going to be looking at the data typically in a sample, keeping in mind that what we care most about is what it tells you or suggests to you about the population. So we want to represent that data visually in such a way that it highlights important facts. Let's start with a simple situation, categorical data. Here's an example of a categorical variable, your political party. It's a multiple choice question you can ask about each person. And I'm going to say that the possible values are Republican, Independent, and Democrat. Notice I could add, Constitution Party or Green Party or something. I could add more choices. I chose to do just these three. And here you can see I have a sample of 63 students. In fact, this is a sample I surveyed Math 217 a couple of years ago. This is actual data. And I think it makes sense that instead of listing 63 times the words Republican, Independent, or Democrat, a more sensible way to summarize the data is to just say how many of the 63 students answered each of the three questions. So that's what I have in the chart here. I have 28 Republicans, 19 Independents, and 16 Democrats answered those three different answers. This is not the best way to summarize that information, however, because remember, I'm typically going to be thinking of this as a sample, maybe a sample of students at Fairfield University, or of statistics students, or I don't know what, maybe of all college students. So if tomorrow I have a class of 20 students, I would not expect to still have 28 Republicans, but I'd expect to have a similar proportion of Republicans. So the interesting thing to look at in terms of inferring information about the population is not the number of each, but the proportion. How do you figure out the proportion? Well, that's pretty easy. The proportion of Republicans is the number of Republicans, which is 28, divided by the total, which is 63, or in other words, 44.4% of the 63 students in this sample were Republican. By the same token, 30.1% were Independent, and 25.4%, which is 16 out of 63, were Democrats. Okay? That's pretty much all there is to say about one categorical variable, and there are two common ways to represent this information visually, which are both pretty straightforward. One is a bar chart. In a bar chart, you put the values of the variable along the x-axis. They don't come in a particular order, so you do whatever order seems convenient. So I have Republican, Independent, and Democrat. And then above each of these, you put a bar, which is proportional to the number or the proportion who give a certain answer. So 44% Republican makes for a tall bar. You have shorter bars for Independent and Democrat. That's pretty straightforward. Notice, and this will come up later, there's a gap between each of the bars. Another way of representing this information visually is with a pie chart, where you draw a big circle and you make a sector of the circle whose proportion of the area is the proportion of each variable. So almost half of that pie is colored blue to represent the Republicans, and the remaining data is almost equally divided between the green for Democrats and the red for Independents. We will not make these charts. They're pretty easy to do in Excel, but we basically won't spend the time on it. We'll expect you to be able to interpret them. This is pretty straightforward. I think most of you already know how to do that. So let's move on to graphical representations of numerical data. Numerical data means numerical variables. Numerical variables, a question whose answer is a number. So I'm going to take as my starting point a quiz score. When you give a quiz, you are taking a sample of students and you're giving a number for each student. So that's a variable. So in this case, I had 10 students. This is imaginary data. 10 students, and clearly the score was on a scale of 1 to 10. The values range from 3 to 10. A little bit of terminology first, which is pretty simple. The smallest data value in your data set is called the minimum, and the largest is called the maximum, and their difference is called the range. So these are parameters or statistics. If it were the whole population, this would be a parameter. Maximum and minimum describe something about the data set. If it's a sample, then they're statistics. They describe or summarize something about the data set. You should be able, and you should stop the tape and make sure you can do it now, to identify the minimum and maximum and range in this case, and then run it when you're ready. Of course, the minimum is 3, that's the lowest value. The maximum is 10, which is the highest value. And that makes the range, their difference, 10 minus 3, or 7. That's pretty straightforward. The simplest way to represent numerical data visually is with a dot plot. In a dot plot, you draw a horizontal number line going from the minimum to the maximum, roughly. Here we went from 0 to 10 instead of 3 to 10. Notice once again, along the x-axis are possible values of the variable. So you should think of those as the scores from 0 to 10, the possible scores. And now you take each data point and you make an X above that line where that data point is. So that first 10 that we see to the left will make an X at the 10 on this to represent that data point, that person's score. There are two 10s. What do you do about that? You stack them on top of each other, right? So we have two X's stacked on top of each other. As you go along, you see that there's going to be two 9s stacked on top of each other, then three 8s, then 7, 5, and 3 will each be by themselves. And now, the value of this visual representation is our brains are really good at processing lots of visual information quickly. And as soon as you glance at that, you see that most of the students got in the 7 to 10 range. There's a big clump there. And there's a few students scattered at lower scores, presumably students who are having a much harder time. Okay, the advantage of a good visual representation is it captures the relevant information at a glance, where you might have been able to see that from the original 10 data points, but if it was a class of 1,000, it might be very hard to see what was going on. It's also true that if it was a class of 1,000, it would be a lot of work to make the dot plot, and it'd be kind of hard to see what was going on with all those X's piled on top of each other. So for large data sets, we don't tend to use dot plots, which means we'll rarely look at a dot plot in this class. Instead, we make histograms, which basically clump together data and then make a dot plot in such a way that there's not an information overload. How do you clump the data together? That's a little bit complicated. You divide it up, the range up, into equal-sized bins. To do that, the first thing you do is pick how many bins you want. This is an art, not a science. It depends on the context and what you want to get out of the data. But a good rule of thumb is to pick something near to the square root of the number of data values. So if you have 100 data points, 10 is a reasonable number of bins to have. If you have 1,000 data points, somewhere in the 30s. We had 10 data points, so 3 or 4 bins is probably all we can do. Once you've decided the number of bins, which is your choice, then the bin size is going to be the range divided by the number of bins. That way each bin will be the same size. That sometimes doesn't work out very nicely. You are allowed to increase the maximum or decrease the minimum a little bit so it all divides evenly. That's a convenience. So for example, here our range is 7. We decided we wanted 4 bins. That wouldn't divide very nicely. So instead, I'm going to move the minimum down from 3 down to 2. So now 10 minus 2 is 8, and 4 divides into that nicely to get 2. So I'm going to have 4 bins, each of width 2. And the way I mark those off is I start at the minimum, so I move my minimum down to 2, and I count up by the bin size. So you go bin min, you add bin size to it, you keep adding bin size to it until you get to bin max. So in our case, the bin boundaries are at 2, 4, 6, 8, and 10, and that divides our range from 2 to 10 up into 4 equal-sized bins. 2 to 4, 4 to 6, 6 to 8, and 8 to 10. And the last step, which is almost trivial, is you just count up how many data points are in each bin. I say almost trivial because you run into a problem if you have a data point which is on a bin boundary. We see here that there are 4 data points bigger than 8, but then those 3 values of 8, should they go in the 8 to 10 bin, or should they go in the 6 to 8 bin? The answer is, you should pick a rule and stick with it. There is no standard convention. I know Excel uses the less common of the 2 conventions, but I never remember which it is. It's never really a big deal. In our case, you can see that I decided that 8 went into the lower bound, so that meant we had 4 things from 8 to 10, that would be the 9s and the 10s. We had 4 things from 6 to 8, that would be the 1, 7, and the 3, 8s. We had 1 thing from 4 to 6, and we had 1 thing from 2 to 4. Okay? So all that process just amounted to taking the data and clumping it together into a smaller number of groups. Having done that, what we do from here on in is easy and is pretty much the same as a dot plot. We again draw a horizontal number line from the bin minimum to the bin maximum, but now instead of putting X's over it, we're going to put bars over it. The height of the bar is proportional to how many points are in that bin. Okay, so we have 2 bins of height 1 and then 2 bars of height 1 and then 2 bars of height 4. Notice the convention. In a bar chart, there was always a gap between the bars. In a histogram, the bars are always pressed up against each other. That's a convention that allows you to quickly tell, otherwise it would be hard, whether you're looking at a histogram of a numerical variable or a bar chart of a categorical variable. Okay, so let me stop because I've told you a bunch of stuff and tell you that we are first going to not worry at all about making histograms, but only about reading and interpreting histograms. That's what I'll talk about now, and that's what you should be mainly focused on. Next, we will learn how to use Excel to make histograms. Excel, all those complicated decisions. How many bins should we have? Should we adjust the bin minimum or maximum? Excel will do for us. It won't do it very well. It will do a crude histogram, but it will be good enough for most of our purposes, which is to get a quick look at the data and a sense of what's going on. We will sometimes step in and tell Excel, no, don't choose your own bin minimums and maximums, I'm going to choose them for you. And in that case, you will need to decide what are reasonable numbers to get the information you want out. Often you'll have to try different things and see what looks best. That is, as I said, more art than science. But there's a sort of triage here. The most important thing that you should begin to have a sense of when you finish this lecture is how to interpret and talk about histograms. The next thing is how to produce simple, crude histograms in Excel without worrying too much about bin size and boundaries. And the third thing is how to adjust those histograms based on the choice of bin size and boundary, which we'll generally do in Excel. All right. So that was a really small data set to make a histogram of, and it wasn't really terribly informative to look at that histogram. Here's some more interesting histograms. Here, previous class of Math 217, I asked the students in a survey how many hours per week they spent exercising. Here's the histogram of that numerical variable. The first thing that leaps out at you as you look at this histogram is its shape. What's its shape? Well, it's got a peak on the left and a very short tail on the left. Right from the peak, as you head left, it goes down briefly and then stops. But on the right, it has a long tail. As you travel right, it gradually decreases, like a slow hill to sled down. What does that shape, the long tail on the right and the short tail on the left and the peak in the middle, what does it tell you about the data? Well, it tells you it's probably pretty hard to read the bins here. I think the peak is 2.75 to 5.5, but it tells you that most people exercise between 0 and 10 hours a week. And there are a small number of people who exercise much more than that. That long tail corresponds to the few people who exercise huge amounts, getting up into the 20 hours a week range. Okay, so that shape tells you interesting things about what that variable looks like in the population. Here's another example. Again, from a survey, I asked Math 217 students what their GPA was in college. Here's the histogram, and you can see it looks pretty much like the mirror image of that. It's still got a peak, but now the peak is on the right side, and the long tail is on the left side. What is that saying? That's saying that college GPAs tend to be on the high side. You can see that most of the data goes from 3 to a little over 4. I think it doesn't really go over 4 because Fairfield GPAs can't go over 4. It's just the last bin. Sizes were chosen by Excel, which isn't very smart, so it didn't go up to 4. Most of the data is in the 3 to 4 range, and there's a handful of students who get significantly lower than that. Third histogram, this actually isn't from my Math 217 data because what I want you to see in this is hard to see unless you have a large data set. But this is a survey, similar survey, big university in Georgia, where they asked students their height. Here's the histogram. Here, the most interesting feature is that it has 2 peaks. If you look closely, there's a peak around 63 inches or something like that, and then a peak around 69 inches. It's still got tails on the left and the right. Neither is terribly long. But the most interesting thing is it's got 2 peaks with a valley in between. Think for a moment about why that is. I bet you can guess. What you're seeing is the effect of gender, right? If I had only shown you the women's data, it would have a single peak, which would be in the low 60s. That's the typical height for women. If I'd shown you only the men's data, it would have a single peak, which would be around 69 or 70, and nicely spread around that. And this double peak comes from superimposing those two, having a population that's a mix of women who tend to be short and men who tend to be tall. You can even, if you're being very observant, you can even guess that there's probably a little bit more men in this sample than women. Why? Because the peak that corresponds to men is a good bit taller than the one that corresponds to women. That is, there are more people in the 70-inch or nearby range and fewer in the 62 or 63 inch, and there's a little bit more people in the upper tail than in the lower tail. Okay, that's the way we want to think about, those are examples of how we'll think about histograms. I want to give you a language for talking about histograms, the kinds of features we just noticed. I want to have names for that we will get used to using. So this is a very important part of the lecture. You will need to be able to walk out of here being able to use this terminology. First word to describe the shape of a histogram is uniform. That's where all the bars are approximately the same height. This rarely occurs in nature, but it frequently occurs in kind of man-made random things, like when you roll a die or use a random number generator. If you think about rolling a die thousands of times and making a histogram, you'd have 6 bars for the numbers 1 through 6. They'd all be about the same height. That's a uniform distribution, or a uniform histogram. Similar word, but very different, is unimodal. This is quite common. It's the most common thing to occur in nature. It's where you have a single peak and tails to the left and right. The first 2 examples, GPA and exercise, were unimodal. The last example, height, was bimodal, where there are 2 distinct peaks. This always means that there are 2 distinct subpopulations in your population. And the first thing you should ask yourself when you see a bimodal distribution, you say, what are the 2 subpopulations? Usually it's obvious. Usually you can guess, or at least take a reasonable shot at guessing. You can think of those 2 subpopulations as a categorical variable, right? Gender is a categorical variable that is related to the numerical variable height. And we're seeing that relationship in the bimodal histogram. And I should caution here that when you call something bimodal, it's because you're seeing 2 distinct peaks that are not just an artifact of the data. Occasionally, especially if you have a small data set, you will see a little wobble where it goes up a little and then down a little, then up. But it's a wobble that might disappear if you change the bin sizes, or might disappear if you just had a little bit larger sample. And we will generally only call it bimodal if the up and down involves enough individuals that it seems clear it wasn't happening by chance. That's a fuzzy distinction, but one we will need to pay attention to. And of course, you can have more than 2 peaks. You can have a multimodal distribution with 3 or 4 or more peaks. Generally, you'll only see that if you have a very large data set. Just as in the case of bimodal, that suggests that there are multiple subpopulations that are different in this variable. Or to put it another way, that there is a non-binary categorical variable that's related to this numerical variable. Okay, so those 4 words, uniform, unimodal, bimodal, multimodal, we will use. And we will also use 3 more words if your data, which describe what the tails look like. If the tails are of approximately the same size on both the left and the right, then you say that the data is symmetric. If it has a long tail on the right and a short tail on the left, you call it skewed right. This comes up a lot in nature. Income and prices, pretty much anything to do with money, will probably be skewed right. The time spent studying or exercising or time spent doing all sorts of tasks tends to be skewed right. Lots of other things. What makes data skewed right? Typically, it's when there's some lower bound that you can't get lower than, which is not too far from the typical data. There you can have an income less than 0, and 0 is not that far from the typical value, but it's possible to have something much bigger than the typical value. There's no upper bound. Likewise, you can't spend less than 0 time studying, but you can spend much more than the typical time spent studying. Skewed left, of course, is where the tail is long to the left and short to the right. There are only a few times where that occurs in nature. The things that I can think of are GPA and test scores and lifespan. In general, it's the same situation as skewed right, where there's an upper bound that the data can't get bigger than, which is reasonably close to a typical value. So GPA is a great example. You can't get higher at Fairfield than a 4.0. You also can't get lower than a 0, but the typical value is somewhere around 3. So that upper bound gets hit closer to the typical value than the lower bound. So GPA is slightly skewed left. Similar things apply to lifespan, where the typical lifespan is only a little bit less than the maximum lifespan. Minimum lifespan is a good bit less than typical. Okay, so we've seen a lot of things. So there's a long list of things you need to know. Most of them are pretty easy. You should know all the terminology around histograms and dot plots. Maximum, minimum, range, dot plot, histogram, and all the bin terminology. Bin size, bin number, bin maximum, bin minimum. You should know, very important, the terms describing histograms. Uniform, unimodal, bimodal, multimodal, and skewed left, skewed right, and symmetric. You should be able to find and interpret proportions for a categorical variable. That's very easy. Just take how many there are, divide by the total. You should be able to calculate maximum, minimum, and range of a data set. Again, pretty easy, unless it's huge. You should be able to produce very simple dot plots. I may ask you to do one with 5 numbers or something. We're not gonna spend time on it. I'm not gonna ask you to produce beautiful dot plots with hundreds of data points, but you should understand what's involved. You should be able to read a dot plot and read a histogram, be able to say things like, oh, that X there means there's somebody whose quiz score was 7. More generally, you should be able to identify the shape of a histogram. Look at a histogram and say, that is unimodal and symmetric. I did not mention, but I should, that the combination, the nicest and most common combination, which is unimodal and symmetric, so one peak and 2 similar sized tails, is often called bell-shaped. If you think about one peak and 2 similar sized tails, it looks like a bell. And if you've heard reference to the bell curve, that's referring to variables which have a bell-shaped distribution. We'll talk more about that in the future. And finally, you should understand what's involved in choosing the bin size and the number of bins. We didn't spend much time on that. You should have the idea that those are decisions. A little more involved. You should be able, when you look at a histogram and you know what the variable is, to suggest explanations for the shape. Why is it skewed right? Why is it bimodal? And even more, if I describe a variable to you, like housing prices in Connecticut, and don't show you the data, you should be able, after you've practiced this, to guess what the shape of the histogram would be. In that case, housing prices, it's pretty clear that it's going to be skewed right. Probably I would expect it to be unimodal, although it could be bimodal if something like single-family versus multi-family houses broke the population up into 2 categories, something like that. Something we haven't done at all yet, which is produce a histogram in Excel, we will do in class, and then I will expect you to be able to do that for the rest of the semester quite frequently. And finally, once we've practiced it a little, you should be able to choose appropriate bin sizes, bin maximums, and bin minimums. As I said, that's very much a matter of context and what you want to get out of the data, and it's more of an art than a science.